This is AP Exam Review, Chapters 1 through 3, Video 3. Here we'll go through some free response questions dealing with stoichiometry. This first one I won't go through, but I'll kind of outline to remind you how to do it. Number 21. We have a reaction, methane gas reacting with chlorine to form dichloromethane and hydrogen chloride. And we're given 25 grams of the methane, which is our first reactant. We're given 2.58 moles of chlorine, our second reactant. We're asked which is the limiting reactant. Remember, to get the limiting reactant, you want to convert each one of these into moles of product. You can either do moles or grams of product, but moles of product will be a shorter problem. And then you would compare which one makes less. The one that makes less is the limiting. So which of these makes less is limiting. And you want to show that calculation. So essentially take both of them, convert them into product, and find your limiting reactant. Part 2 says calculate the number of moles of excess remaining after the limiting reactant has been consumed. What you would do here is you would subtract your two numbers. So the two numbers that you got here, you would subtract them, and this is how much would be made if you had enough of the limiting. So what you have to do then, after you subtract these two numbers, you would have to convert this back into excess reactants. So think through that one. Go ahead and work through it. This will be a good review of some stoichiometry limiting reactants problem. Let me go through number 22 and solve it with you. So this one actually is an empirical formula problem, and it deals with a compound that contains 4 elements: carbon, nitrogen, hydrogen, oxygen. We have 1.2356 grams of the sample of the compound. So here's how much total compound we have. Now we burn it in excess oxygen. Remember, anytime you burn it in excess oxygen, you're effectively reacting this compound plus O2, whichever, this is a hydrocarbon, and what you get is you get CO2 plus H2O. Now if you analyze both carbon dioxide and water, if you analyze these for their carbon content and for their hydrogen content, you can actually find out how much original carbon, how much original hydrogen was in this amount right here. And that's what they tell us. So they said whenever it's burned in excess oxygen, we have 2.241 grams of CO2 formed. So the first thing they ask us in part A is how much carbon is in this original compound. Well, the way we're going to find out is all the carbon from the original compound went into CO2 based on this combustion analysis. So if we can pull out of here, out of this CO2, if we can pull out the carbon, we'll know how much carbon. And this is easily done since the percent of carbon in CO2 is a set number. In fact, the percent of carbon in CO2 is simply the ratio of carbon, the mass of carbon, which is 1201, to the mass of the whole thing, which is 4401. This is essentially the molar mass of carbon dioxide. This is the ratio of carbon in carbon dioxide. And if we multiply this ratio by the total, we'll be able to pull out 2.241 grams. We'll be able to pull out the carbon of this total. This essentially is the percent of carbon in carbon dioxide. So hopefully that makes sense, but if you do this calculation, you should get yourself 0.6116 grams of carbon. Now, part 2 says when the compound is analyzed for nitrogen only, the mass percent of nitrogen is found to be 28.84%. What's the mass of nitrogen in the original? This is easy enough since we're told that the nitrogen makes up 28% of this. Just multiply this amount, 1.2359, by 0.2884. In other words, percent divided by 100. So just remove the percent, get the decimal, and this should get us a value of 0.3564 grams of nitrogen. And next, they ask us to determine the mass of oxygen in the original compound. Now they tell us that we have also some hydrogen. The hydrogen amount they told us here is 0.0648. So now since we have 3 of the 4, if we subtract all 3 from the original, we'll get what's left over, in other words, oxygen. So take the original amount, which is 1.2359, and subtract what we know so far. So we know carbon, which subtracts 6, 11, 6. Subtract also nitrogen, 0.3564, and also subtract hydrogen, which is the rest of it, 0.0648, and this should give us a total of 0.2031. And this is our mass of oxygen. So these are the three amounts that we've determined. The fourth amount is hydrogen. Now all four of these will be used now to determine the empirical formula of the compound. Remember, to get the empirical formula, the poem again is percent to mass, mass to mole, divide by smol, and multiply till whole. So we'll have to undergo each one of these. Now we're given mass, so we actually begin at the mass step. And as you'll see, we'll only have to use two of these. So let me pull it up a bit and let's try. So we have here our mass of carbon was 0.6116 grams. So percent to mass, these are already in mass, so mass to mole. We have to divide by molar mass to get to mole. So we're converting to mole. A mole of carbon is actually 1201 grams, and that gets us 0.05092 moles of carbon. This would be carbon. Next, we'll do the same thing with nitrogen. So we had 0.3564 grams of nitrogen. A mole of nitrogen weighs 1401 grams. That gets us 0.02544 moles of nitrogen. Next, we have hydrogen. And of hydrogen, we had 0.0648. And I should really be labeling these. This is hydrogen, this is carbon, this is nitrogen. Hydrogen is mass, a mole of hydrogen is 1.01 grams. That gets us almost the same number. To be exact, 0.06416 moles of hydrogen. And finally, oxygen. We began with 0.2031 grams of oxygen. Oxygen's molar mass is 1600. And if you divide that number, you'll get 0.01269 moles of oxygen. So these are the relative mole amounts of the elements in this compound. Now to even these out, that's what the divide by small step does. So if we divide all these by the smallest, we'll kind of even them out and make them in terms of just one of them, the smallest, which makes the numbers clean. So this oxygen is the smallest number, so we'll end up dividing each one of these by the moles of oxygen, by 0.01269, 0.01269, 0.01269, and 0.01269. So if we do that, we get 1 mole of oxygen, which is going to be our set number. If you divide these two numbers, you see we have roughly from 12 to 60, it's roughly 5 times as much. So this gets us 5 moles of hydrogen. This is roughly double, so this we get 2 moles of nitrogen. And we roughly get, looks like 4 moles of carbon. Now, if these numbers weren't exact, if you do the calculation, and if you find that these numbers aren't exact, maybe if this was 4.25 or something, or maybe this was, if this were 2.3, then you'd have to multiply till whole. In this case, these numbers come out to be pretty even, and we can get our formula from all these, and our formula turns out to be C4, N2, H5, O. So this is the empirical formula of this compound. Be able to do empirical formula calculations. And finally, E asks us a different compound which has the empirical formula CH2Br, has a molar mass of 188 grams per mole. What's the molecular formula? Now remember, molecular formula is bigger than the empirical formula. It's a multiple bigger. So 2 times bigger, 3, 4, 5 times bigger. And the way we can find out how much bigger is we can compare these two masses. So if we get the molar mass of CH2Br, we find that the molar mass is about 93.9. which looks to me like it's about 2 times smaller than the molecular, which means the molecular is 2 times bigger. So from here to 88, 188, you have to multiply by 2, which means our formula, CH2Br multiplied by 2, becomes C2H4Br2. Everything essentially is 2 times bigger. And this is the molecular formula. Now, a feature of the molecular formula is that it could be oftentimes reduced. So this can be reduced down. A feature of the empirical formula, it can no longer be reduced. It's the most reduced formula. In fact, you can't reduce this because of the one on oxygen. So make sense of this. Try the question on the back as well. I will actually just outline it real quick. So 23 does a similar calculation, but now with a hydrate. So what you're going to do is trying to figure out the moles of water in this hydrate just by using some lab data. I want you guys to try this on your own, and then we'll take questions as needed in class. So come with those next time we see each other.